I'll be continuing discussion on two-dimensional point groups, and in this lecture we'll have a look at how we can use matrices to represent symmetry operations. So we'll start this as matrix representation. So matrix representation of symmetry operations. So let's consider in the xy plane and we can imagine that the z axis is normal to this figure, and we are considering Cartesian coordinates. Take a point xy, and I am not writing the z coordinate because we are just working in the xy plane, and after some rotation of, let us say, theta, this point xy rotates to a new position x prime y prime, and let us say the distance of these 2 points from the origin is r, and we have rotated through an angle of theta in the counterclockwise direction. Now, I can write the new coordinates in the following way. I can write down x prime equals r cos of alpha plus theta. Similarly, y prime can be written as r of sine alpha plus theta. Now, I can expand this equation, the two equations, and one can write x prime to be equal to r of cos alpha cos theta minus r sin alpha sin theta. Similarly, y prime, if I expand the sin term, would be r sin alpha cos theta plus r cos alpha sin theta. And if we look at these two equations, let us look at the term r cos alpha. Now, what is r cos alpha? R cos alpha clearly from the figure has to be equal to x. Similarly, r sin alpha again from this figure would be equal to y. So, this is y and this is x. So, one can write x prime to be equal to x cos theta minus y sin theta, y prime to be equal to x sin theta plus y cos theta. And if one were to write z prime, well, z prime, since we are only moving in the xy plane, z prime does not change. So, the z axis will remain as simply z. Now, let me just add another term here to x prime equation. Let me call this as 0 multiplied by z. Similarly, for y prime also 0 multiplied by z, and for z prime let me add two terms, 0 multiplied by x plus 0 multiplied by y plus z. So, all the three equations now have three terms, and one can now write the same equation in the form of symmetry matrix or in the form of as a matrix representation. So, one writes x prime, y prime, z prime. This is a column matrix, and then there is a 3 by 3 matrix, cos theta minus sin theta 0, sine theta, cos theta 0, and from the third equation I will have 0, 0, and basically z is being multiplied by 1. So, therefore, this term would be 1 and the column vector x, y, z. So, this becomes my rotation matrix, and I will denote it as r z theta, that is the z axis is the rotation axis itself, or we can even consider just the point at the origin is basically the point of rotation normal to this xy plane. Similarly, one can write the rotation matrices r x theta, that means now the rotation axis is the x axis and we are rotating in the yz plane. So, this you should be able to do it yourself. 1, 0, 0, 0 cos theta minus sin theta, then I have 0 sin theta cos theta. So, this is the rotation matrix around the x axis, and around the y axis r y theta, the rotation matrix becomes, so here we have the rotation in the xz plane, cos theta 0, sin theta 0, 1, 0, minus sin theta 0, cos theta. Knowing these three axes, we can actually now determine rotation about any arbitrary axis as well. So, for example, suppose I have in 3 dimensions in the Cartesian coordinates, and let us say my rotation axis is this one and I have to rotate through theta, and the angle that this rotation axis makes with the x axis is alpha and the axis itself is in the xy plane. We have this, then I can find the rotation about this axis in the following manner. I first do a rotation about the z axis, and let us say that this alpha is actually 45 degrees. Then I do a rotation of 45 degrees, or rather I do a rotation of minus 45. So, this is a rotation, if you look along the z axis, this is going to be a clockwise rotation. So, after this rotation, the rotation axis will coincide with the x axis. So, the first operation that one does is rz 45 degrees minus 45 degrees, because this is a clockwise rotation. So, clockwise is negative, counterclockwise is positive. Following this, now I can do the required rotation of theta about the x axis, for which we already know the matrix. So, we know the matrix for z axis also, we know the matrix for the x axis also. So, I have two matrices I have written, and then I have to bring back the rotation axis to its original position, which means again I do a rotation, but this time around the z axis, but this time a positive 45 degrees, that is counterclockwise to, then the axis will come back to its original position, and the matrix thus formed by multiplying 3 matrices here would be the rotation matrix for this particular axis. Similarly, one can do it along other arbitrary directions, rotations around those directions, but every time we will have to bring that axis to coincide with the x axis or the y axis or the z axis, and then do the required rotation and then do the opposite operations to bring that axis back to its original position. But I will not try to multiply these numbers right now, we do not need it right now. Next, this thing is, let us now see how this rotation matrices representation will help us with the group. So, for example, let us consider group 2, which we had considered in the last lecture. So, group 2, if you recall, it is the identity operation followed by a rotation of 180 degrees, a pi. Now, we can, what would be the identity operation in terms of matrices? Would be the identity matrix. So, the identity operation is 1 0 0 0 1 0 0 0 1, and identity matrix when multiplied into this vector x y z. So, how do you multiply matrices? Take the top row, take this row and multiply it into this column, and then multiply the corresponding elements in the row and the columns and then add them up. And so, the first is what I will get would be x, because the other elements are 0. So, I will have x plus 0 into y plus 0 into z, and you are left with x. Similarly, take the second row and this column, multiplying the corresponding elements, we get y. And finally, take the third row, multiply it into again the same column of x, y, z, and one would get z. So, as you can see that the indices x, y and z do not change on multiplying by the identity operation, and that is to be expected. So, my first element in the group, the identity, I have the identity matrix. For the second operation, I already have, and we are saying we are rotating about z. So, I already have the rotation matrix for this r z theta. So, now if I, let us just look at what would be this a pi operation. I will write it as r z pi and insert the value of pi into the sin theta cos theta terms, and clearly one would get minus 1 0 0 0 minus 1 0 0 0 1. Now, for example, if I have to now find out what happens if we do two operations in this group. So, I do r z pi followed it up with again r z pi. This is a trivial operation anyway. I would get the identity matrix when I multiply the two matrices. Let me take another example. Let us take group 3, which would be 1 identity operation of 120 degrees, a 2 pi by 3 operation of 240 degrees, but I will write it as minus 120 degrees, minus 2 pi by 3. So, this is what would be the 3 elements. Now, I already know what is the element 1. Let us write, instead of this, I will write this as r z 2 pi by 3 r z minus 2 pi by 3, and one would get r z plus 2 pi by 3. If I insert it again into the cos theta sin theta term, angle of 120 degrees. So, I am going to get minus half minus root 3 upon 2 0, root 3 upon 2 minus half 0, 0, 0, 1. Similarly, for Rz minus 2 pi by 3, the terms would be minus half root 3 upon 2, 0, minus root 3 upon 2, minus half, 0, 0, 0, 1. So, I have all the 3 elements now in the form of matrices, and one can very easily fill up the group table. This is Rz minus 2 pi upon 3, and out here also this is going to be minus 2 pi upon 3. If I fill this element would be 1, this is obviously Rz 2 pi upon 3, Rz minus 2 pi upon 3, Rz 2 pi upon 3, Rz minus 2 pi upon 3. Now, where are the other identities? Well, Rz 2 pi upon 3 followed by minus 2 pi upon 3 plus 120 degrees minus 120, it is clearly the identity will be 1, and if we take these 2 matrices and multiply, we would get a result of 1. Similarly, here also it will be 1. If I multiply, let us say the matrices Rz 2 pi by 3, Rz 2 pi upon 3, the 2 matrices basically same matrices, if I multiply, my result will be a matrix which would be basically minus 120 degrees. We will get this as the matrix on this multiplication. So, this would be equal to Rz minus 2 pi upon 3. So, this Rz minus 2 pi upon 3, and finally, in this last cell we multiply Rz minus 2 pi by 3 into the same matrix. One would then get this as the result, which would be Rz 2 pi upon 3. So, just as an example, let me actually multiply one example I will take and multiply Rz 2 pi upon 3 times Rz 2 pi upon 3. Now, this can be written as minus half minus root 3 upon 2, 0, root 3 upon 2, minus half, 0, 0, 0, 1, and the same matrix repeated again, minus half minus root 3 upon 2, 0, root 3 upon 2, minus half, 0, 0, 0, 1. And let us see what result one gets. So, what do we do? Take the first row of the matrix on the left, multiply into the leftmost column of the second matrix. So, minus half goes into minus half. So, this will be multiplied with this. So, that will give you plus 1 upon 4 minus root 3 upon 2 into root 3 upon 2, that will give me minus, so I am multiplying this element into this element. So, this will give me minus 3 upon 4 plus 1 upon 4, and I will be left with minus half, because the third element 0 into 0 gives me back to 0. Now, come to again the first row and now the second column of the second matrix. Same thing, minus half into minus root 3 upon 2, that is plus 3 upon 4, minus root 3 upon 2, and then I multiply. So, minus half into minus root 3 upon 2, that is 3 upon 4, and I will be left with plus root 3 upon 2. So, that I think you should be able to see quite clearly. And the first row into the third column, the first two elements out here are 0. So, that is 0 plus 0, and the third element in the row of the first matrix is 0. So, therefore, this remains as 0. And similarly, next time what one does is take the second row, first column of the second matrix, do the multiplication, and one will get minus half, 0, and the third row into the first element 0, third row into the second column is 0, and then finally third row into the third column I will get 1. So, this becomes the resulting matrix. Now, if I compare this matrix with this particular one RZ minus 2 upon 3, you will see that these two matrices are identical, and so the resulting operation is minus 120 degrees. And same way you can multiply the other matrices and you can fill the group multiplication table. So, I also need to talk about symmetry operations and the symmetry operations related to reflection. Those reflection, and we will produce reflection matrices, which I will take it up in the next lecture.